Welcome to Brain Vision.
Have another problem where we have a let's see here, we have a steam plant. Let me, book isn't loading up here for some reason. Let me get that loaded up here. Oh goodness. Um, so we have another ranking cycle basically. Um, So that we have, then let's see here. Contents, let me get to the problem. 11. Okay, scroll back up here. Lots of problems in chapter 11 or 10. Okay, let's see here. Problem 20. A steam power plant operate on a simple ideal ranking cycle between the pressures of, let's see here, 1,250 psia and 2 psia. Let's see here. We have 75 pound mass per second flowing through. We want the moisture content here. They say we don't want it to exceed 10%. So we need the quality factor to be 90% there, so that we have at no more than 10% by mass water in the mix here. Let's see here. We know, again, we're told that we have a, let's see here. We're going to assume, I don't see where they actually said it, but I think we need to assume that we have some, since we're not given any efficiency numbers here, as far as, yeah, to use, we have to figure that these are ideal, that we're assuming that these are isentropic here, or we can't proceed. So we're going to say those are isentropic, turbine and pump. So let's see here. Again, we can use at 1 here, it's saturated liquid. So we can get the enthalpy and the specific volume. We can figure out the work because we have a incompressible fluid and we're increasing the pressure from P2 to P1 or P1 to P2. And so we get 3.75 BTU per pound mass. That allows us then to do an energy balance on the pump, and we figure out the enthalpy going out of the pump is 97.77 pound mass per BTU. And again, this would be an ideal pump. Then at point 4 here, we know that if we'll set the quality factor to 90%, and we know the pressure, so we can figure out the enthalpy and the entropy there. We can then, if we know that, again, this is isentropic, so S3 equals S4. So now we have S3 and we have P3. So then we can figure out what the temperature and the enthalpy are at state 3 here, coming into the turbine. And then we can figure out the rate of heat in here, or from here to here. And that winds up being, about 120,000 BTU per pound mass. Oh no, that's 120,000 BTU per second. Sorry, we multiplied through by the mass flow rate. Out, we look at the enthalpy change from here to here, and we get about 69,000 BTU per second. And so in this problem, they just wanted us to figure out what the efficiency was. We could figure out what the net workout is, but we don't really need to do that to get the thermal efficiency, because we know that the net work out is just Q in minus Q out, and then doing a little math here, we separate and we get 1 minus Q out, Q dot out over Q dot in, and that in then becomes 42%. So we could have taken the difference here and gotten the net work out or net power out, but we didn't need to. by just using this form. Again, you had w dot net all over q dot in, but w dot net is q dot in minus q dot out all over q dot in. So we get 1 minus, we get this expression. Again, you've seen that hopefully many, many times by now.